So free.
Capitol Hill to work out a compromise.
Soccer bopper, more fun than a pillow fight. Blow 'em up.
Please stand by for our feature presentation on electronic temperature controls. Brought to you by Urinal. With Urinal, the world is your bathroom. And now we begin our feature presentation.
Electronic temperature controls for HVACR and cooking equipment. In this slide presentation, we'll talk about their advantages over mechanical controls, the common types of temperature sensing devices used in both, and a basic electronic temperature control circuit design. The market for electronic temperature controls and temperature sensors is huge and very competitive. There are many proprietary designs of electronic temperature controls. There are many models of temperature sensors manufactured to fulfill the market's needs. Additionally, some sensors are integral to a temperature control board, such as an HVAC system. Some are remotely located, such as in refrigeration and cooking equipment. The intent of this presentation merely provides some fundamental understanding of electronic temperature controls and temperature sensors. Electronic temperature controls, thermostats, have largely replaced mechanical thermostats for obvious advantages. As this table shows, electronic temperature controls are accurate to plus or minus 1 degree. Mechanical may be accurate to 5-degree increments or even greater. Electronic controls are programmable for various reasons that suit their design. The mechanical ones constantly require monitoring. For electronic, when used correctly, programmable thermostats are touted as saving homeowners 10 to 30% on their heating and cooling bills. Obviously, mechanical controls would have higher energy bills. Few drawbacks on electronic ones, you have to have a power source for them to work, whether it be a battery, such as in your HVAC thermostat in your home, or otherwise be powered from the appliance. Mechanical controls require no power to operate. Setup of electronic controls can be complicated, otherwise mechanical ones are sometimes preferred for their ease of use since the user only has to turn a dial. First, we'll talk about the mechanical type of temperature sensors. The first basic one is bimetal. Two metals bonded together with different temperature coefficients of expansion. So you have copper and iron strip are equal lengths at room temperature. When they're unbonded but heated, copper will expand greater than the iron will. Now, if you bond them together, obviously it would bend. You clamp one end down and have the other end as the actuating end to it, then this can be used to operate plunger, two contacts, and so on and so forth. Here's one that you would typically find in old home thermostats. It's a spiral bimetal element. It uses a mercury bulb as the electrical contact to turn the HVAC system on or off. This is a very common one, a snap disc, sometimes called a click-on, used as a thermal overload protectors, roll-out switches, and defrost thermostats. Now, it has the contacts there, it has a plunger, and down in here, you'll have the actual bimetal disc. In this case, it's showing it as concave, probably a normal state. However, if it gets too hot, then the bimetal disc will snap into a convex state, and the plunger will push up and actuate these contacts to, in this case, open them. The snap disc is not adjustable. It's simply manufactured to function at the temperature at which the manufacturer specifies for the equipment. Okay, bimetal strip thermostats. Used in heaters, toasters, cooktops, ovens, dryers, clothes irons, some refrigerators, and freezers, and also used as compressor and motor overloads in some cases. It shows a temperature adjustment cam, which is adjusted by a rotating stem. You have a set of contacts and a bimetal strip. The cam could be set so that the bimetal strip would have to be a greater degree or a lesser degree based upon the desired setting in order for the contacts to open or close, depending on how it's designed. Here's another example of the bimetal strip. This is enclosed. There's a knob, stem with a calibration screw right there, and a micro switch that's operated by the bimetal strip. Strut and tube. It's not a common item, but They are in use in some water heaters, commercial fryers, and hot food well. They're known to be rather expensive, but also known to be the most accurate mechanical control on the market. The strut and tube is comprised of two basic parts: the outer shell, made of high expanding metal, and the strut assembly, made of low expanding metal. A pair of electrical contacts is mounted on the strut assembly and installed in the shell under tension or compression. Each end of the strut assembly is mechanically connected to the ends of the shell, and net change of force is produced on the strut assembly as the shell expands or contracts with changing temperature. The temperature at which the contacts make or break can be regulated by a temperature adjusting sleeve. Here are some other examples of the strut and tube. Each of these have some mechanical means in order to adjust the temperature. It should be noted that these can be designed to also make or break at a fixed temperature to serve as a high limit, like in a commercial fryer. Another type of mechanical control is a bellows, which is a charged bulb and capillary. These are used in package terminal air conditioners, window air conditioners, refrigeration, and large cooking equipment. So in this illustration, you have your bulb, you have your capillary, and then you have a bellows. I should probably add that it's also charged with the same gas. Up here you have the contact arm. You have the opposing spring tension, which opposes the action of the bellows. Here you have your adjustment stem. Where it is set determines how much the bellows must expand or contract in order to close these electrical contacts. Here's an example of one to be used in a walk-in cooler or freezer. And here's the bulb and the capillary, which is charged with a refrigerant or some type of gas that will cause the bellows to expand or contract as it's heated or cooled. Here's one for a reach-in refrigerator or freezer. It lacks a bulb, but it has a capillary tube. Same idea. It's charged with a gas, operates a bellows inside the body of the thermostat. Here's another one. I believe this one is used for a cooking appliance. Well, here's one that's not even electrical. It's got a bulb and capillary, but this is used in a gas valve, which so happens to also be used in a cooking appliance. Same idea. It's a mechanical control using a bellows. Okay, electronic. Electronic temperature sensors are sometimes referred to as a temperature transducer, a temperature transmitter, but most often called a temperature probe. Three categories most commonly used in heating and cooling systems are the thermocouple, an RTD, which stands for resistance temperature detector, and a thermistor. First, we'll talk about a thermocouple. The thermocouple consists of two wires of dissimilar metals welded together to form a sensing junction. At the other end of the thermocouple signal wires, usually within the temperature control board, is another junction called a reference junction. Heating the sensing junction generates a thermoelectric potential, or electromotive force, EMF, proportional to the temperature difference between the two junctions. The output is a millivolt level DC voltage. The temperature control board interprets that millivolt output as a temperature detected at its sensing tip. Here's an electrical symbol of one. In this case, it shows the positive and negative polarities, and this represents the sensing junction. Here's one that's actually used in a thermometer, but that voltmeter probably has gradients on it to represent temperature. And in this case, there's a sensing end with a chromel and alumel wires. Here's the reference point, or the reference junction. And then from there on, you just need basic copper wiring to transmit that circuit to the voltmeter. Something that should be clarified here, in this illustration, you have a flame, two dissimilar metals, and a millivolt output. This represents a thermocouple that would be used in a pilot ignition circuit. Temperature sensing thermocouple should not be confused with the flame sensing thermocouples used for proving flame in standing pilot output systems. They both generate DC voltages, but for different reasons, so they're each designed differently. Thermocouples are simple and familiar. However, they require a special compensation for their nonlinear output. Well, here's a graph, two graphs actually. An ideal output of a thermocouple would basically be, for each degree of increase in temperature, you would have an equal level of output from the sensor. So it would be linear. A thermocouple is not linear, however. The ideal response is in black, but the actual response is shown here in red, so it has nonlinearity error. There are circuits designed to correct this. They're more complex than we will get to in this presentation. Thermocouples come in many types. Here's a graph showing those many types. We'll be talking about a few of these in a second. That's most common. It has many standards of design based upon the national or international market: American, British, German, French, and Japanese, and American original. This seems to be the most common, IEC 584. This chart basically will just confuse you. You're rarely going to be able to use it to translate what type of thermocouple you're looking at. Usually you would need to consult with the manufacturer to determine what type of thermocouple they put in it. So, thermocouples come in many types. However, the two most commonly used in HVACR and cooking equipment are the type J. It's made of an iron Constantan junction, has restricted temperature range than a type K, but higher sensitivity, which means a DC output per degree of temperature change. It's the most common type of thermocouple used in cooking equipment applications. The type K is made of a chromel-alumel junction. Its range is suitable for HVAC and refrigeration. It so happens to be the type used by most digital test equipment as well. So here we have a picture of one that's probably used for a meter. It's a bead probe, and these terminals, which one's wider than the other, obviously would be for the sake of polarity. You can barely see the positive and a negative there. That would be plugged into a meter. Here's one that's got color-coded connections on it, and it probably would indicate positive and negative somewhere, and a screw-in button, probably for a surface sensing device like a flat-top grill. Here's another one with a surface sensing type of thing with a lug type connection. So notice the color differences. And here's one that, well, it says positive, so obviously the other was negative, and it's just looked like a regular probe. Your probe tip is in here, the sensing element. Okay, for testing, depends on type of thermocouple. The type J, accurate testing requires using a DC voltmeter capable of reading tenths of a millivolt. Temperatures at the sensing and reference junctions must be measured and noted. The probe's millivolt DC output read by the voltmeter can then be cross-referenced using a manufacturer-supplied chart indicating what temperature the probe is seeing. Such charts are rarely provided. If they are, it's only with an understanding that your voltmeter is capable of reading such a low voltage range within the thermocouple's output range. Most meters aren't capable of measuring DC volts at such a low range. Otherwise, the manufacturer might provide some alternate method to test whether a probe or the temperature control board is the culprit. Aside from a good visual inspection, then, a simple test is for a possible open thermocouple. An ohmmeter can provide an idea of the probe's general condition. A good thermocouple should read just a few ohms. Otherwise, if it reads open, then it probably is indeed bad. However, this resistance test does not provide information regarding the probe's accuracy. The second type of thermocouple is type K. As mentioned before, type K thermocouples happen to also be used by most digital testing equipment. For checking this type of probe in an appliance, simply set the voltmeter to read temperature, the temperature setting on your voltometer. Obviously, this would be probably a digital meter. Isolate the probe from its circuit. Connect the meter test leads to the probe leads while observing proper polarity, red to positive, black to negative. The voltometer will display what the temperature is sensing. The next type of sensor is the RTD. RTDs are constructed of dissimilar metals that have a repeatable electrical resistance versus temperature relationship and operating temperature range. The R versus T relationship is defined as the amount of resistance change of the sensor per degree of temperature change. The dissimilar RTD wires, which makes it work, are purely metal materials, typically platinum, nickel, or copper. These materials have an accurate resistance-to-temperature relationship, which is used to provide an indication of the temperature. RTDs, which have a higher accuracy and repeatability, are slowly replacing thermocouples in industrial applications. Now, some RTDs have a positive temperature coefficient, so as temperature increases, resistance increases as well. Some RTDs have a negative temperature coefficient, so as temperature increases, resistance decreases. Overall, there are multiple variations of each type, depending upon the temperature range and its application. However, a common example used in HVACR and cooking equipment are several variations of the PT100. Now, the PT stands for its positive temperature coefficient type, and the 100 is that it has a resistance of 100 ohms at 32 degrees Fahrenheit nominal. Room temperature, this particular probe so happens to read almost 110 ohms, and room temperature is 77 degrees typically. RTDs can be 2, 3, or 4 wire leads. 3 and 4 wire leads are used to compensate for factors affecting accuracy. Examples being unusually long probe lead lengths back to the controller, possible electrical noise, and etc. Here's an electrical symbol for an RTD. It looks like a resistor with an arrow through it. Here is a diagram showing the 2, 3, and 4 wire configurations. We'll get too much into that, but that basically probe will come with 2, 3, or 4 wires, and in the secondary instrument will only be set up so it can use that particular type of a probe. Here's pictures of some that are out on the market. Looks like these are for sensing liquid or liquid medium of some types. It's got pipe fitting. Here's the 3 wire. Looks like all these are 3 wire. And the various types of connections that they can use. These are sometimes referred to as banana plugs. Those are very typical, and you can't plug other types of sensors in those type of plugs, so it kind of meets a standard there. You can't mistakenly plug in the wrong type of probe. Kind of a bead probe there, in a way, small sensing tip. A lot of these probes will look very much alike. The thermocouples we looked at earlier, and these, sometimes when you look at them, they look identical. Here's the diagram showing the various ways in which they're constructed. Some are flat. I have never seen a flat thermocouple or a thermistor, which we'll get to in a minute, but I have seen flat RTDs. Again, showing the flat versus the round, and another diagram showing how the tip is sealed in various methods. So is the RTD linear? Yes. Here is an RTD diagram. It's showing the comparison between the thermocouple, which we've spoken of, and a thermistor. The RTD, for all intents and purposes, is the most linear temperature sensor. It might need some correction, but not much. Testing methods for RTDs is simple and straightforward. You isolate the RTD from its control board. For 3 or 4 wire probes, short the light colors together before testing. Connect an ohmmeter to the 2 leads or sets of leads. Read the space or heating, cooling, and medium temperature using an accurate digital thermometer. Do this with your thermometer probe in close proximity to the RTD's probe. Using the temperature read on your thermometer and the resistance of the RTD being tested, compare the results to the numbers provided on a manufacturer's cross-reference chart for that RTD, if available. An alternate method that you can use is, again, knowing what type of probe it is. In this case, we're going to talk about that PT100. You can disconnect the RTD from the temperature control board and dismount the probe. Take the tip of the probe and immerse it into an ice bath for 2 minutes. Take a resistance reading of the RTD. If its resistance is not 100 ohms, RTD is defective and must be replaced. And the third probe we're going to talk about is a thermistor. The name is a blend of the words thermal and resistor. It's presently the most popular sensor out there. It's generally made of a semiconducting ceramic and polymer material, while RTDs use pure metal. Thermistors exhibit a large change in resistance proportional to a small change in temperature. A typical thermistor shows a negative temperature coefficient, but some manufacturers of thermistors do offer positive coefficient thermistors as well. For NTC types, resistance drops dramatically and non-linearly with temperature. Here's a chart showing that. This is a 10 kiloohm NTC thermistor, and you can see how quickly the resistance drops in just a matter of 30 degrees right there. Sensitivity of a thermistor is many times that of an RTD, but useful temperature ranges on some types are limited. With high sensitivity, a thermistor may change resistance by tens of ohms per degree temperature change versus a fraction of an ohm for RTDs. Thermistors can be used for point sensing because the thermistor bead can be made the size of a pin head for small sensing areas. Here are some symbols of them, like a hockey stick. going through a box, and it has the positive T, obviously for the positive temperature coefficient, or negative T. Another variation would be the resistor-looking symbol with a hockey stick through it. Here's some examples of the sensing tips, which appear they might be able to be soldered to a board, such as a HVAC thermostat. Here's one that is a bulkhead mount. Here's one that is a sensor for a fluid medium with a pipe thread on it. Thermistors are usually characterized by their base resistance at room temperature nominal, which is normally 77 degrees Fahrenheit, as this provides a convenient reference point. Thermistors are made to many specified nominal ratings. As far as testing methods, it's also simple and straightforward. Isolate the thermistor from its control board, connect an ohm meter to the two thermistor leads, read the heating or cooling medium temperature using an accurate digital thermometer. With your thermometer probe in close proximity to the thermistor's probe, using the temperature read on your thermometer and the resistance of the thermistor being tested, compare the results to the numbers provided on a manufacturer's cross-reference chart for that thermistor. Here's an example of one of those charts, and actually this example uses a very commonly used thermistor. It's called a 100 kilo ohm thermistor, and it does not show the nominal rating of 77 degrees. If it did in Fahrenheit, then we would be seeing resistance of 100 kilo ohms. This one here actually happens to be for an oven, so it takes big jumps. You notice that from 100 degrees Fahrenheit, it still has 53,000 ohms. But then you go to 200 degrees, it's dropped all the way down to 7,500 ohms. And you go to 300 degrees, it's down to 1,728 ohms. So a huge drop in resistance, degree of temperature change. All right, so when you're testing one, if there's a sizable difference in resistance read when compared to the actual temperature, then the probe is bad. If the probe tests good, then the temperature control board is bad. When troubleshooting electronic temperature sensors, here's some things to remember. Realize that electronic sensors tend to look alike. You have a thermocouple versus an RTD versus a thermistor. Which one is it? Well, when in doubt, call the manufacturer. When troubleshooting, be aware that sensors are susceptible to their working environment, so they can fail as a result of that, such as heat, moisture, corrosion, vibration, and other forces. When troubleshooting, first check the probe's integrity through a visual inspection. Check its tip, check the wire sheathing, check the wires, look for hard bends and turns, look for loose connections, look for corrosion. Sometimes just wiggling the wires will reveal a problem is with the probe. If the probe appears compromised, replace it. Using your test equipment, use a digital multimeter and don't touch the probe's leads with your hands, because then you can alter what you're trying to read with your meter. When practical, test under the conditions which the problem occurs. Good examples in an oven. If you have a probe at room temperature, it might read fine, but you put it inside the oven at 350 degrees, it might have an issue, and you would be wanting to test it under those circumstances. Now that we have explored the electronic sensors, let's put one to work in a control circuit. So here we're designing an electronic temperature control, using the following format to design this circuit. First, there'll be an input. It will be the device that's sensing temperature of the space. Next will be the control in order to translate that input into a desired output, such as if it's too cold in here, we're going to turn on the heat. So in creating the input, this input is the part that senses temperature, converts it to a voltage. Firstly, we need a thermistor. This alters its resistance according to temperature. As it heats up, resistance lowers. This type has a negative temperature coefficient. This particular type used here has a resistance of 5 kilo ohms at 77 degrees Fahrenheit. So creating the input, we want a voltage to represent the temperature, but the sensor only changes in resistance. So we add another resistor, and then we're going to form a potential divider or voltage divider network. So when this voltage divider or potential divider network is connected across the supply, the output produces a voltage proportional to the temperature. The hotter the temperature becomes, the higher the voltage will be. To elaborate on that somewhat, taking a look at this diagram, we have 9 volts positive applied here and 0 volts right there. So a voltmeter would read 9 volts between here and here. You have 2 resistors connected in series. R2 is a fixed resistor, 6.8 kiloohms. R1 is your thermistor, and its resistance varies according to temperature. So as temperature goes up, its resistance goes down. This is all where you need to understand voltage drop. Understanding that if this resistance goes down and this stays the same, then the amount of voltage at this point right here would be higher. If we go the other way, and again, this stays the same, this resistance goes up, then the realized voltage at this point will go down. So once again, the hotter it gets, the higher the voltage. So now we're going to create the control. The voltage from the input changes only small amounts. We need to use a device that is very sensitive to changes in the input. An operational amplifier is an ideal choice. Very common device used for not only temperature control, but also for systems that sense light when the sun goes down and turns on your porch light, or power sensors that are used to control your automatic garage door in case somebody walks underneath it and it stops the door, those sort of things. So anyway, this is a very common operational amplifier. And here, the one type we're using here is specifically designed for this application, is known as a comparator. This is what one looks like. The word comparator means to compare, and it's what it's going to do here in a moment. The connections for the comparator is shown. The rule on how a comparator operates is if the voltage in positive is greater than the voltage in negative, then the output is turned on. So we're looking at the diagram, voltage in positive right here and voltage in negative. So if we connect the signal from the sensor, the thermistor, the voltage in positive, we can connect a voltage to voltage in negative as a comparison. To produce this, we're going to be creating a reference voltage to compare against. To do that, we need another potential divider. And the one we're going to explain here in just a second uses a potentiometer. It's just a variable resistor. Here it says the range is about 0.75 volts to 8¼ volts. Now, how do we derive this? That's quite a span from close to 0 volts at one point and almost the entire 9 volts that we have applied in this circuit. Let's take a look at these resistors. You have a 1 kilo ohm resistor here, 1 kilo ohm resistor here, and those two are rather small when compared to the variable resistor in the middle at 10 kilo ohms. Now, any variable resistor has a sweep. That's the part that varies. You move that sweep from one end to the other, and it changes the amount of resistance with regards to this point to this point and this point to this point. Let's move the sweep all the way down to the bottom. If it was at the bottom, then basically you'd have 0 ohms resistance at that point. So we 10,000 ohms here to here, and then on up to the R3 resistor of 1 kilo ohm. That would give you 11,000 ohms. So you have 1,000 ohms here and 11,000 ohms from here and here. And that is the greatest chunk of resistance in this entire circuit. So that's dropping the most voltage at the top half. And basically then if we're picking up at the bottom half where the sweep is at only 1 kilo ohm, then you're probably getting a realized voltage at its minimum voltage drop of the 0.75 volts. On the other hand, if you take that sweep and you go from one end and sweep it all the way up to the other and turn it all the way up, we'll forget everything in the middle. Then your sweep has that full 10,000 ohms between the top and the bottom, and add that to the 1 kilo ohm down here, well, then you have a total of 11,000 ohms going on between the sweep and the 0 point in the circuit. 11,000 ohms there and only 1 kilo ohm there. So you're dropping your most voltage across the bottom half of this circuit. That means that we're picking up at the reference voltage or the sweep 8¼ volts. And that will be inputted to the comparator, as we'll see in a second. Now we're going to connect this to the comparator. There's your operator's selection using the variable resistor. Here's your output from the thermistor that changes based upon temperature. The difference between these two, if this one is higher, we're going to turn the thing on. R5 has been added to provide for hysteresis. It means that it has a slightly different switch on and switch off points to prevent chattering. So if your switch on and switch off points are too close to each other, it would probably rapidly fluctuate between the on and off state, and that's undesirable, obviously. And so they try to differentiate the 2 points so that there is no chatter or rapid fluctuation of the control. Now we're going to create the output. We want to switch on a relay when the circuit activates. But the output from the comparator is not powerful enough. We need a driver. The most basic one is a transistor driver. In this case, we need around 150 milliamps for the relay. That number right there is a standard transistor number, which can deliver around 500 milliamps, so it'll be suitable. There's your transistor with your base, emitter, and collector. The transistor needs a couple of additional components to protect it. It is a small device and vulnerable to damage. Resistor R6 restricts the current flow into the transistor, protecting it from damage. There's R6 to the base. Notice the addition of a diode D1. This is to prevent damage caused by high EMF voltages generated in the relay coil. So there's your relay coil, and there is the diode. This is pretty standard whenever you've got a relay or a set of contactors connected to electronic control. To explain it real quick, let's say we have the relay coil energized. It has a magnetic field around it when it's energized. Whenever you de-energize a coil, that magnetic field collapses. As it collapses, it will actually induce a voltage into its own self across its own set of coils, and it becomes a power source. And if you didn't have a place to allow that power or that voltage to get back and return back to itself, because it is momentarily, in a fleeting moment, a power source, then it would otherwise go through the electronics and damage them. So this is what we have so far. You have your input coming from the thermistor, and it's the voltage divider network. Temperature causes the resistance to the thermistor to fluctuate. Then you have the control, which is your variable resistor that establishes your set point where you desire your temperature to be. The difference between the thermistor's resistance and the variable resistor's resistance ultimately will determine the inputs to the comparator. The comparator is comparing those and the voltages that are resultant from these two voltage divider networks. If it so happens that the temperature in your house is too high and it causes the resistance of R1 thermistor to go down, then the voltage resulting from this divider network will be, and as it becomes higher when compared to your reference, the output to this comparator is turned on. The output is turned on, it goes to the transistor, it biases the transistor on to energize the relay, and the relay will operate and control your heating or cooling device. We'll watch this squeeze together now. We'll connect them all. But there you go. Input, control, and output. Oh, and they're going to add one more thing. Because we need to have the DC to be steady in an electronic circuit. After all, that 9-volt DC source probably came from an AC source originally that was stepped down and rectified. The voltage supply needs to be decoupled. This means putting a capacitor across the supply to smooth it and improve circuit performance. There's your capacitor right there. So, with all of that preceding information covered, you won't be expected to go right out and build a control board or even troubleshoot a board at its component level. That's not your job as a field service technician. However, having some fundamental understanding of what makes them work will allow you to troubleshoot electronic temperature control boards with confidence and competence. Furthermore, when a temperature control is designed with remotely located probes or, in rare instances, a potentiometer that isn't integral to the control board, you can effectively narrow down the problem to whether it's the probe, the board, or that separately installed potentiometer.